Okay,
You're
our
good.
project is the high-speed training using binary neural networks, and our project mentor is Dr. Richard Martin. So this is our team. We have Sachin, Daniel, myself, Daniel, Tommy, and Serena. So the goal for our project, currently machine learning is very slow because it uses floating point numbers, which take about 1 million transistors. Uh, Recent work from another paper has shown that using a simpler representation of numbers like fixed point uses only around 300,000 transistors. So this uses less power and it's a simpler arithmetic operation than a floating point. And so our goal is to create and measure neural networks using only binary or fixed point numbers for both training and inference.
So what's the difference between a floating point number and a fixed point number? So floating point numbers are the current standard for machine learning and other computer science applications. And it's stored in a computer similar to like in scientific notation. So it's extremely precise and it has the ability to store a large range of numbers. It contains a sign bit, which in the 4.5 times 10 to the 6 example above, it's positive. The exponent section is the 6, and also the mantissa is the 4.5. And these sections need to be normalized, and that takes up a lot of resources. And it uses about 1 million transistors, versus a fixed point number is basically a regular decimal number. So it contains an integer part, which is the part to the left of the decimal point, and a fraction part, which is the part to the right of the decimal point. And it only uses transistors in the magnitude of thousands, which is much more efficient. But one downside of this is that it has a limited range of numbers. And this is a consideration that we have to make and test in order to use our model. There are also two different activation functions that we're using. An activation function basically helps the network learn patterns and it decides what to fire to the next neuron. So the sigmoid activation function, you can see here, it's 1 over 1 plus e to the negative x. It's more complex than ReLU, but it's less efficient. And as you can see in the picture of the graph, the outputs are constrained from 0 to 1 on the y-axis versus the ReLU, which is less complex and more efficient. So you can see on the graph, it's 0 to the left of, the output is 0 to the left of 0, and output is x to the right of 0. So it's a lot less complex than sigmoid. But as you can see, the outputs approach infinity, and this leads to poor accuracy. So that requires another layer like softmax to function accurately.
The datasets that we used are the MNIST digits and fashion. Both of them contain 28 by 28 grayscale images and are easy to incorporate. However, the MNIST digits dataset is easy to train and highly implemented with near perfect accuracy, while the MNIST fashion dataset is difficult to train and more applicable for CV tasks. For the first 5 weeks of our project, we adapted the GitHub repository for GoNN, which builds a simple neural network in the programming language Go. We also plotted the maxima and minima of the floating point weights to get dynamic range, as shown by the graphs below. We also checked for accuracy plateau and implemented a fixed point matrix library, which is a 64-bit representation with a sign bit, 50 bits preceding point, and 48 bits following.
From week 6 through 9, we were mostly going through those considerations we were talking about before. So we were checking to see which activation functions would properly work for us and changing those activation functions to meet our criteria. So we were adapting sigmoid such that it would work properly with the fixed point representation. We were analyzing sort of the effects of sort of like truncating our numbers and how that would affect our accuracy. Such that like see how much precision we could drop without necessarily changing our accuracy. And we also began implementation of ReLU activation to see if that would work considerably more than our more complex sigmoid function. We sort of, on top of that, we applied sort of our existing fixed point schema and our fixed point models to the MNIST digits and fashion databases to check their accuracy as a whole, to see if our, to check and see if our concept of applying fixed point models would work in sort of real world scenarios. And on top of that, began collecting and analyzing the accuracy and sort of ranges for for both of these models to compare them in the future. Along this way, we ran into some issues. At first, we found out that our fixed point range, or the range of our of these algorithms on these data sets, does not necessarily converge over an extended period of time, and we need to find a workable range at which there would be some like usable accuracy for our fixed point representation to have sort of a range through which we could work on. On top of that, as explained earlier, our ReLU, which would theoretically be a lot more efficient, required an additional softmax layer added to our model in order to function that we needed to begin building and considering. Finally, our sigmoid function, which we were using for the vast majority of the project, we found that it did not work under a lot of the, did not work unedited along the, with our 64-bit fixed point representation, as using the sigmoid function would overflow our fixed point representation in a lot of cases and was like smoothened and like altered in order to function well. As you can see, sort of these two graphs show the sort of like different sorts of discontinuities we were getting from the overflowing of our sigmoid function.
Yeah, and so regardless of all these issues, at most, compared to a traditional floating point type of network, it was about a 3% drop in accuracy, which is actually extremely promising. And another promising result was that the dynamic range tended to be small, even though it did converge. And what that means is that within the weight matrices, we had a higher maximum and a lower minimum, and that continued to diverge apart, but it still remained relatively small. So it was about like plus 10 and minus 10. So what that means is that we don't actually need very large integer portions of our numbers. The main consideration lies in precision. And so we had to actually test and see what truncating precision actually, in what ways it would affect our model's accuracy. And as it turns out, truncating up to about 39 bits off of a floating point maintains most of the accuracy of the model. So we don't actually need most of our precision. And that was an immense promising factor of our testing. And also, as you can see on the right, the accuracy eventually plateaus, even though the dynamic range continues to increase. So again, we don't actually need to use this wide range. At some point, it can be cut off, and we still achieve most of the accuracy that we need. So further research into this topic may be applying our fixed point schema to other databases, like, I don't know, CFAR 10, for example. We could also adapt our code to a larger variety of neural networks, like convolutionals and recurrent neural networks. And then also further the testing of our implementation of the ReLU function. So overall, in conclusion, we have shown that there's a way to bridge this almost existing gap in between like these high level software packages and these low hardware implementations. And so in doing so, we can save a lot of power and potentially speed up the training of neural networks. So we do have a website if anybody's interested in checking that out. And that's our project. Any questions?